Hello everyone and welcome to MV Tutors. I'm Tselo and I'll be going through the proofs that you need to know or that can be examinable in the maths exam. Okay, so for both paper 1 and paper 2. Fortunately for you, for paper 1, the only proofs that I can really examine you on are for the sum of the arithmetic series and also the geometric series. Okay, but for paper 2, well, in the trigonometry and Euclidean section, there are quite a few proofs that you need to know. So let's just go over them and see. All right, so like I said here is a list. Oh, before I even go far, guys, please don't forget to like our videos and also subscribe to our channel. And yeah, while you're at it, just click on the notification bell. And when we load more videos, you'll be alerted, all right? And if you want a personal session with us, please go to our website www.mvtutors.co.za and make a booking, all right, for a free consultation. Okay, so what proofs do you need to know? Like I said, for paper 1, it is derivations of the formulae for the sum of the arithmetic and geometric series, including the sum to infinity. All right, and then for paper 2, well, for trigonometry, you should be able to derive the basic identities. Okay, so how do we get that tan theta is equal to sine theta over cos theta? Also, the sine squared theta plus cos squared theta is equal to 1. The other derivation is for the compound and double angle formulae. Okay, also once we have cos A minus B being equal to cos A, cos B plus sine A, or sine alpha, not A, alpha and sine beta, like we can get also other compound angle formulae, okay, just from that cos alpha minus beta, all right, and also the derivations of the sine, cosine, and area rules. Okay, and then for Euclidean geometry, proofs of circle theorems. Okay, so we need to show that the line drawn from the center of a circle perpendicular to a chord bisects the chord. Okay, and also show that or prove that the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at the circle. Okay, angles subtended by a chord of the circle on the same side of the chord are equal. Two opposite angles of a cyclic chord are supplementary. Two tangents drawn to a circle from the same point outside the circle are equal in length. All right, I'm sure you're like, what is all of that? But we'll go through the proofs, guys, the ones that are examinable. Okay, and then the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. And then also proofs of triangle theorems. Okay, so proportionality theorem for one, a line drawn parallel to one side of a triangle divides the other two sides proportionally. Equiangular triangles are similar, and triangles of sides in proportion are similar, as well as Pythagoras' theorem using similarity. So yeah, we're going to be going through the proofs, so brace yourself. I thought it's better to do it in one video so that you know that once you're done with them, you're done and you can focus on practicing other problems. I know proofs are one of those things that you leave to the last minute or never even get to it. And then come the exam, you're there scratching your head like, how do we do this again? So let us be better prepared next time. Okay, so we're going to start with paper 1 and we're going to start with the arithmetic series. Okay, let us do it. So before I show you how to do the proof, I'm going to start with an actual example, okay, so that from there we can then see how we can derive the formula. So at the end, we either want to get to this formula, okay, or there's another one where what am I doing? So it's a shorter version where you have n over 2 and then you have the first term and the last term. So I'm going to show you how to derive both of them. All right, So let us say we have this series over here. Remember, there's a difference between a series and a sequence. I discussed that in the video. Okay, so yeah, let's say you have this series over here. Okay, so I can see that the first term that I have there is 3. Okay, and then also if I look at the common difference, I see that to get from 3 to 7, I need to add 4. And also going forward, I'm going to have to add 4 all the time. So my common difference would be 4. All right. And if I wanted to know, so I know my first number, right? It's 3. If I wanted to know, this is my last term over here. Okay. If I wanted to know what position the last term is without having to count, okay, so it's easy to count, but I mean, if you have many numbers, you do not have time to count. So what we're going to do to get the position of the last term, we're going to use the term formula. So you know that the term formula is equal to A plus N plus N minus 1 D. Okay, and what is A? We said it's 3. Our last term, the term is actually 39. And then we're looking for the position. So basically we're looking for N. And we know that our common difference is plus 4. Okay, so what I'm going to do, yeah, that should be a positive there. So if I were to multiply it out, I would have 4n minus 4. So 3 minus 4 is actually negative 1 plus 4n. Okay, and all of that has been equal to 39. And then when I now solve for n, I am going to get minus 1 going to the other side will be plus 1. So 39 plus 1, that's going to be 40. So now the last term's position is 10. Okay, so now that we have the position, what we're going to do, we're going to actually find the sum of the 10 terms. Okay, so we first start from the minimum to the maximum. Okay, the sum of the first terms, we get 3 plus 7 plus 15, 11 and 15 and all of that. Let me save time by copying instead of writing it out again. Okay, so paste it over here. All right, so what we're going to do, we're going to write initially from ascending order, okay, from the first to the last term. And then we're also going to write in descending order. Okay, this I need to write out from the last term to the first term. So I'm going to go 39 plus 35 plus 31 plus 27 plus 23 plus 19 plus 15, 11, 7, and 3. Okay, so once I'm done doing that, I am now going to add the 2 rows. Okay, so this is basically my first equation, and that will be my second equation. Okay, so what I do, I add my first and my second equation. Okay, so if I add them, I will be getting 2 times the sum of the 10 terms. Okay, and then 3 plus 39, okay, that will be 42. 7 plus 35, that will also be 42. Okay, 11 plus 31, that will be 42. So you can see the trend here. We keep on getting 42. So I need to make sure it's actually 10 42s. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Ooh, what a long thing to do. So now we basically have 2 is 10, which is equal to 10 times 42, because there are 42 tens, right? No, there are 10 42s. There are 10 42s. Yes. So now, if I were then to divide by this 2, I would get 10 over 2 times 42. And this it actually, if you look at our equations over here, let me put them nearby so that we can see, compare side by side. But if you look at this, okay, this sort of like, it mimics the sum formula. Okay, so if you were to sum up everything in here, that would give you 42, okay, or a plus l, that would give you 42. And that is true because the first term is 3 and the last term is 39, and 3 plus 39 is actually 42. Same here, if you're going to take the first term, which is 3, and you know you have 10 terms minus 1, that's 9, and the difference is 4, so here you're going to get 6. 9 times 4 is 36, so basically that is 42. So we're going to use that very same idea, but this time we're going to use variables. We're not going to have numbers. I just wanted to show you first by using numbers that we can actually get the proof. Okay, so now let us use values. No, not values. We just used values. We're just going to use now variables. Okay, we're going to do the same thing. All right. So if we want to prove that the sum of an arithmetic series is equal to all of this, I know that A, well, that represents the first term, right, of my series, and D, that represents the difference, the common difference. Okay, so there's always a common difference in an arithmetic series. Okay, and then N represents the nth term, if I could say, so the placing basically of your term in the series. Okay, if I could say, and L represents the last term. Okay, and we show that we actually get the last term by using the term formula. Okay, so we can definitely get the last term by using the term formula. Okay, so let us begin. So you have your sum over there, okay, to however terms that you have. All right, and then your first term would be A. Your second term would be A plus D, because that is the common difference. Your third term would be A plus 3D. Fourth term would be A plus 4D, until, okay? And then you get to your last term. Okay, the term before the last term would be it would be D, because now if I have my last term, then if I'm starting from the right to go into the left, I'm gonna have to subtract the common difference. Okay, so that's the last term, the second last term, and then the third last term. Okay, and then yeah, we have plus, and then there are terms in between. Okay, so now we are going from the smallest to the largest. Okay, and then on the other side we flip it around, we go from the last to the smallest, or the beginning rather. So then we're gonna have L minus D, and why did I put a 3 there? It should be plus 2D. Okay, so A plus 2D. All right, so we're adding that, and then we have L minus 2D, all the middle terms, and then we have A plus 2D, and then we have A plus D, and we have A. Okay, so now if I were to add the two rows, okay, making, let me just put double there, double lines. Okay, so again, if I were to make this my first equation and that my second equation, I'm going to get the sum of 1 plus 2. Okay, so that would be 2 is n. Okay, and then if I add the corresponding ones, I have a plus l here. Okay, then I have a plus d plus l minus d. So I have a plus l again. Okay, because the d's cancel out. Even there I have a plus l. Okay, and it continues a plus l all throughout. Okay, but as for how many a plus l's we have, well, that is, up until the nth term. Okay, so now we can then say, like we had done here before, we are here now at this step, so we can say then 2 Sn is equal to, we don't know how many these a plus l's are, but hey, there we are. So now we can say Sn is n over 2 a plus l, and we have proved this one over there. And we know that l is actually equal to the nth term, which is a plus n minus 1d. So we can actually substitute a plus n minus 1d in the place of l. And when we do that, we have n over 2, okay, a plus n minus 1d. And when we simplify that, we have n over 2, all right? We have 2a plus n minus 1d. Okay, and do you see that it now gives us the other form, where it is n over 2, 2a, n minus 1d. Okay, so we have proved both. Okay, and that is it for the proof of the arithmetic terms. Okay, the sum of the arithmetic formula. So now we're going to go over to the geometric. Okay, and we're going to finish off with the sum to infinity. All right. Alrighty, so for the geometric series, we need to prove that the sum of the terms is equal to a times 1 minus r to the power n, or over 1 minus r, or this side, okay, where the 1 and the r to the power n are swapped. Okay, so I've also decided to start with us using values, and then we'll get to the actual proof. Alright, so for us to get from 2 to 6, okay, firstly, the first term, which is a, that is equal to 2, right? And then our common ratio, okay, for us to get from 2 to 6, we need to multiply by 3. And also to get from 6 to 18, we need to multiply by 3 as well. So r is positive 3, okay? And what else are we missing? Okay, the number of terms here, we have the sum 1, 2, 3, 4, 5. Okay, we have 5 number of terms. Yeah, so let's see what we can do with that. Similar to the arithmetic series, we're gonna get the sum, okay, and we're gonna write all those values down. So we're gonna have 2 plus 6, 18, 54, and 162. Okay, so what we're going to do then, okay, so this is equation 1. For us to get equation 2, we are going to multiply all these values by 3, okay, because our common ratio is 3, all right? So we're actually going to say r times equation 1. So our r is 3, okay? And then what we're going to do, we are going to shift. So I know that 2 times 3 would be 6. So I'm going to write the 6 there. So we're going to shift to the right, okay? And the reason why we do that is so that when you start subtracting, things cancel nicely, okay? So 2 times 3 would be 6. 6 times 3 would be 18. 18 times 3 would be 54. And, you know, it will go on and on like that. And then 162 times 3, okay, 3 times 2, that is 6. 6 times 3, that's 18. Carry 1. So that's going to be 486. Okay, I was just lazy to take the calculator out. So we have that. And now, let me just draw that. Ooh. Okay. So, yeah. So actually, I shouldn't have put S in there because we know that N is 5, right? So it should be S now. My 5 and my S look the same. All right, so what we're going to do, we're going to subtract. So with the arithmetic series, we actually added, but here we're going to subtract. So this is my second formula, right? So we're going to take the first formula and subtract the second formula. And in so doing, if I were to say this 1 minus 3, I'm going to get negative 2 is 5. Okay, then 2 minus 0 over here, that would be 2. And then, 6 minus 6 would be 0. So I have 0, 0, 0, 0. And then I have negative 4, 8, 6. Okay, so we're going to take negative 2 is 5 is equal to 2 minus 486. So I'm going to actually have negative 484. Okay, so yeah, and then if I actually work out that sum, it's going to be negative 484 all over 2, negative 2. And then we get what? We are going to get 2, 4, 2. Okay, so we're going to do something similar, but now instead of actual values, we're going to use variables, okay? The A, the R's, the N's, and so forth. So now, we don't know how many terms we have, so it's going to be Sn, okay? We have our first term, which will be A. We have our second term, so because we have the common ratio, we keep multiplying by R. So we're going to have AR. Then we're going to have the third term, which is AR squared. And then we're going to add many numbers, okay? So then our last term is actually going to be AR n minus 1, okay? I hope you get that. And then if we're moving to the left, okay, it's going to be AR n minus 2, okay? And yeah, so that would be the first row. So what would happen in the second row? So this is my first equation. And then when we get to the second part, remember we multiplied by the common ratio here. So we're going to have R Sn. And also we shifted, the first term. But we're going to continue multiplying by R. So A times R, that would be AR. Okay, AR times R, that would be AR squared. And we have all those terms in the middle. And then AR n minus 2 times R. Well, we're going to have, if I do it on the side, I'm going to have R, right, n minus 2 times R, which will be adding a 1 there. So it would be AR no, actually, sorry, let me start it from the back. If I started from the back, if I take this one here, okay, and I multiply by R, this will definitely be ARN, because it's going to be minus 1 plus 1, and so the ones will cancel out, and then I have just R to the power n, okay? And if I move to the left, okay, I would have to subtract a 1 there, okay? And then I'll get over here, which is R, yeah. So that's basically what would happen. Okay, and then we have 0 over here. So if we add all of those up, or rather subtract, remember we're going to take our first equation, and we are going to subtract the second equation from the first. Okay, so it's going to be 1 minus 2. First equation minus the second equation. So I will have there a negative, no, this would be Sn minus r Sn, okay? Yeah, so it's, yeah, okay, and then I would have a minus 0, which is just a, and then I would have all of these terms subtracting until we get here. Okay, so we're gonna have 0, 0, 0, 0, and then we're gonna have a negative 8r to the power n. Okay, so now we actually have Sn 1 minus r here if I take out the common factor, which is Sn. Okay, and then I have a minus a r to the power n. Okay, so still, if I were to take out the common factor on the right side of the equation, I would take out a. So I would have 1 minus r to the power n. Okay, and if I were to make Sn the subject of my formula, I would have 1 minus rn, okay, and then 1 minus r. And that looks like our equation over here. Where is it? Yes, a 1 minus rn, 1 minus r. Is that the one? Yes, that is the one. So basically that is how you would prove for the geometric series. So there are two forms of this equation. Okay, so I only gave you, which one did I give you? 1 minus r. Okay, so I gave you this one. So for you to get the second one, what you would do, you would take out the negative value. Okay, so if I were to take out a negative, okay, I have a negative a outside, then I would have r to the power n minus 1, okay, and if I take a negative out as well, I would have r minus 1. So to simplify that, the negatives would cancel, so I have a rn minus 1 all over r minus 1. Okay, let me just make sure I have the right stuff. Let's just see, put it next to each other. And the conditions are there as well, that r should not be equal to 1. That is a good, shouldn't forget to put that condition. Okay, so let's see. So yes, we have the first one, we have already proved, and the second one, we already proved as well. So we should just remember that r should not be equal to 1, because if r is equal to 1, then you have an undefined formula, and you're never going to get to a solution. If you put that in your calculator, you're going to get a math error. Okay, so I hope you guys understood the arithmetic and now the geometric. Okay, I hope using values first kind of helped. Yeah, so that is for the geometric, and now we're going to head over to the sum to infinity. Alrighty, so now we're going to look at the sum to infinity, okay, proving the formula for the sum to infinity of a geometric series. So we're still under geometric series. So the sum to infinity, basically it is the first term over 1 minus the common ratio, and provided that the common ratio is in between -1 and 1, not equal to either -1 or 1, okay, between. So basically r is a fraction or a decimal. Okay, yes, so remember, wrote here PS. I want to say remember, I'm not sure if PS is that. But the sum for the geometric series, remember we had it as s to the n, okay, but in this case we're saying that n is actually tending to infinity. So what happens? So if n were to approach infinity, what would happen to r to the power n? Okay, so we have the basically, remember we said that r should be a fraction or a decimal. So if you have a number in between negative 1 and 1, okay, so after negative 1 you get what? Negative 0.9, right? And you go all the way to 0, and then ultimately you get to 0.9. So hence I say it's a decimal, it's a fraction. Okay, so r is a very small number. So here's how I'm going to put it. Okay, so n tends to r. Therefore, what would r be? If we say r, so if we say r to the power n, what does that mean? Okay, so r, we said it's a very small number, or it's a fraction. Okay, just gonna say very small number in between minus 1 and 1, and or rather let's just say it's a small number. Let me not say very. Let me just rather say small number. Okay, so it's a small number, or rather let me just say it's a fraction. So I take a fraction, okay, that I know is less than 1. Sorry, it is bigger than negative 1 and less than 1. Yeah, that was right. So we have that fraction, and we're taking that fraction to the power infinity. If you're going to take a small number, okay, and take it to the power infinity, it's going to be even smaller. It will tend to 0 ultimately. And you can try that on your calculator. Put a fraction, okay, whatever, 1 over something, and then take it to the highest number. Say 1 over 2, or whatever, 1 over 3, anything, 1 over whatever. And then, want to take that 1 over 2, for example, take it to the power 1,000, and you'll see that that number gets smaller and smaller. Okay, maybe I should get the calculator quickly and then I'll show you. Okay, so let us take a fraction. Let's say 1 over 2, that is the biggest, well, not really the biggest, but yeah. So 1 over 2, and we take it to the power, not 2, but take it to the power 1,000. We're just starting off with 1,000. So already, as you can see, delete. Already, as you can see, you have such a small number, to the power negative 304. That is 10 times, yeah, but this number 933 times 10 to the power negative 304, that's a very small number. Okay, if we were to increase that to maybe, I don't know, 1 million, I mean, it's so small that, ultimately it would be 0. Okay, so hence we would say that if you take a fraction or a decimal and you round it off, we could have even put the 0.9. Okay, 0.99, let's say that 0.99. Still, it's a very small number. So the more you tend to infinity, your value here, Rn, it will definitely tend to 0. So as a result, we would then say the sum to infinity would be equal to a, okay? Then I have 1 minus 0, and then I would have 1 minus r. Okay, so r is a very small fraction, not 0. So 1 minus r, okay? Okay, let me not say very small. I like saying very small. R is a number between negative 1 and 1, all right? So then I would have a over 1 minus r. And the condition as well, like we said, is that r should be in between negative 1 and 1. Okay, so that's basically how you prove it. You're basically going to take your normal geometric series formula, okay, and then you're just basically going to substitute the infinity where n is, okay, and then you'll see things will start to unfold and work out. And that's basically the proofs for paper 1 that is completed. Okay, I hope it was fine, and I hope that if they should they actually take it out, you'll be able to handle it with ease. Alright, so please don't forget to like our videos and also subscribe to our channel. And while you're at it, click on the notification bell to receive notifications when we load more videos. If you would like a session with us privately, please do visit our website and make a booking at www.mvtutors.co.za. Okay, so we're done with paper 1, proofs, okay, for the arithmetic, geometric, for the arithmetic and the geometric series, okay. So now for paper 2, okay, when it talks about these identities, tan theta is equal to sine theta over cos theta, this is just something that you need to know. You don't have to prove it. As well as sine squared theta plus cos squared theta is equal to 1 is really something that you should know. What I would advise is, okay, so we're done with paper 1. What I would advise is you should know how to rewrite them both. Okay, so for example, tan theta, you could have 1 over tan theta, and you should know that that would be equal to cos theta over sine theta. With the second one as well, you could then say that sine squared theta is equal to 1 minus cos squared theta, as well as cos squared theta can be equal to 1 minus sine squared theta. So you can rewrite it in those ways. Okay. Also, when it talks about, okay, I'm going to skip this for now. But when it talks about the derivations of the sine, cosine, and area rules, it's basically saying you must know the formulas, and they are given in the formula sheet. Okay, so you don't have to cram it, so you can relax. Now when it comes to the compound and double angle formulae, okay, so with the compound as well, angle, you must just know what they are, and they are given in the formula sheet. So the compound, it's those ones where we have the angle, if you have sine alpha plus beta, sine alpha minus beta, and then you have cos, okay, cos alpha plus beta, and then you have cos alpha minus beta. Okay, so basically just know them, recognize them. Remember that sine alpha plus beta will be equal to sine alpha cos beta plus cos alpha sine beta. Okay, and the opposite for sine alpha minus beta, so it'd be sine alpha cos beta minus cos alpha sine beta. When it comes to cos, if you have cos alpha plus beta, you'll have cos alpha cos beta, and if you have a plus here, it's going to be a minus. Okay, so it'll be cos cos minus sine sine. Okay, as well as with the negative here, you'll have cos alpha cos beta plus sine alpha sine beta. They are given in the formula sheet. The one that you should know how to derive, which other ones can be derived from, would be the cos alpha minus beta. So that is the one we're actually going to focus on. That is the one that you need to know how to prove. As a matter of fact, it came out in the November 2021 exam where you had to prove it. Okay, so that is the one. And when you look at double angles as well, with double angles, it's a matter of applying the compound angles. So we're going to look at that as well. So that is our focus, the compound and double angle formulae, okay? Having to prove cos alpha minus beta is equal to that, and that you can get other expressions from that one, okay? As well as looking at the double angle formulae and how we actually get it, all right? So let us try, let us attempt it. Okay. So I'm going to start with the compound angle. Alrighty, so that's the compound angle, and we're going to prove the one that they've given us here, cos alpha minus beta. Cos alpha minus beta, how do we know that it's actually cos alpha cos beta plus sine alpha sine beta? What are we going to do to show and prove that? So the compound angle cos alpha minus beta that is equal to cos alpha, cos beta, plus sine alpha, sine beta. All right, so for you to actually prove this one, it's going to take forever. And that proof is actually not examinable. Okay, if we just recap here, it says that derivations of all compound and double angle formulae, accepting that cos alpha minus beta is equal to, cos alpha, cos beta plus sine alpha, sine beta. So you are already starting from the standpoint by accepting this expression over here. Okay, so you don't have to prove this one. That would take quite a long while, because you need to sketch on the Cartesian plane, put some angles in there, do hectic stuff. Okay, so they wouldn't ask that. As far as I'm concerned, or I know, that proof is not going to be examinable. But from this one, from cos alpha minus beta, you will be expected to show that cos alpha plus beta is equal to this. You'll need to also show that sine alpha plus beta is equal to that. And lastly, show that sine alpha minus beta is what I've shown over there, which is what we are going to do right now. Okay, and after doing that, we would have been almost done with trigonometry. Yes. So what would you do here? Okay, we are saying that cos alpha minus beta, from this proof over here that you don't need to know, we can get the others. So let us begin. So if I have cos alpha plus beta, I'm going to write it such that I have angle number 1 minus angle number 2. Okay, so I will have the cos, so I will have alpha minus, minus beta, such that if I were to multiply both negatives, I will still get a positive beta. Okay, so I took out a negative, so the beta had to be negative. Okay, and what does that do? Okay, then I will have cos alpha as well as cos negative beta, and that negative there will then become a plus sine alpha as well as sine negative beta. Okay, so if I were to simplify it, I would still have cos alpha here. Now the cos of a negative angle is equal to a positive. Okay, that did not make sense the way I said it. But whenever you have a negative angle, when it comes to cos, you're gonna get a positive answer. And why is that? If you were to draw the cos graph, you know that it starts somewhere here and it ends like that. Also this side. So it is symmetric about the y-axis. So even if you had a negative 30 degrees and you have a positive 30 degrees, you will have the same answer, which would be positive. Okay, so unlike sine and tan, where sine of a negative angle is equal to negative sine that angle, for cos, if you have cos of a negative angle, it'll just be positive cos of that angle. If we have sine of a negative angle, you would have negative sine of that angle, as well as with tan of a negative angle, that would be negative tan of that angle. Okay, I hope you know that. So we can just remove that and continue with the proof. So therefore, I would have cos beta there, okay? And then I have a plus over here, okay? And then I have sine alpha. But like I said, sine of a negative angle is equal to negative sine beta. Okay, then if I were to finalize it, it would be cos alpha, cos beta. This negative would come out, so it's negative sine alpha, sine beta. And we are there at our answer, cos alpha, cos beta minus sine alpha, sine beta. So this one is proved, okay? The main thing that we did there, we changed this positive, okay, and made it a negative. Okay, that's what we did. So now let's have a look at the second one. Okay. All right, so for B, what you're going to do, in order to change sine alpha plus beta into a cos, you're going to have to use co-ratios. Okay, I hope you remember them. So we have sine alpha plus beta. Okay, we're going to use a co-ratio, so we're going to have cos there. And that cos then will be the 90 minus the angle. Okay. Why am I choosing 90 minus instead of 90 plus? Well, if it's 90 plus, it falls into the second quadrant where sine is positive, so you'll still get a positive cos. But if I were to change cos to sine and I say 90 plus, cos would be negative in the second quadrant. So just to be safe, we're going to use acute angles. So it's better if I say 90 minus the angle instead of 90 plus the angle. Okay. And besides, the reason why we're using 90 minus ultimately, really, is because we are using this main expression over here, where it's one angle minus the other one. Okay, so I think that's a better reason to give, that we have one angle subtracting another one. Okay, so we're using co-ratios to do that. So if I were to do that, what would happen? Okay, yeah, so I would have, let me just, should I multiply? Yes, let me multiply it out. So I have cos 90 minus alpha. I'll have that as my one angle, and then minus the beta. Okay, okay, and then if I were to simplify that again, so I have then cos 90 minus alpha cos negative beta. Okay, so because we changed it to a cos, now I have cos, and because I had a negative there, I need a positive over here. So now I have sine 90 minus alpha and multiplied by sine negative beta. Okay, so what would cos 90 minus alpha be? Well, 90 minus the alpha means we're in the second quadrant, and that cos and 90 will actually change to a sine. Okay, and we have sine alpha. And then I would have cos negative beta. We already talked about it. Cos of a negative angle is just equal to a positive cos of that angle. All right, so we already have sine alpha and cos beta. And then we have a plus there. Sine 90 minus theta. The sine and the 90 would change to a cos. Okay, and 90 minus theta means it's in the first quadrant, so it is positive. And then we have an alpha there. And then we actually have, sorry guys, no. I have been making a mistake here. So we actually have a minus and we have a positive beta. So this should be positive. Okay, it's not a negative beta. It's just simply cos beta. Okay, which is cool. So here as well, it's not a negative. It's just sine beta. Okay, because I see it wasn't getting to the answer ultimately. So sine 90 minus the alpha, that would be cos alpha, and then we have sine beta over there. And yeah, by so doing, we already have our answer there at the top, so we managed to prove it. Okay, now we get to the last bit. All right, and we're going to show with that using the cos alpha minus beta, how to actually prove it so that we can get this answer over here. So again, because we have sine alpha minus beta, I am going to get a co-ratio because I want cos. All right, so sine alpha minus beta is equal to cos 90 minus alpha minus beta. Okay, close that big bracket over there. So I have 90 minus alpha plus beta. Okay, and similar to what we did there at B, I will be taking cos 90 minus alpha, okay, as one angle. And then because, guys, we need to maintain this one angle minus the other angle story, okay? So I'm going to take a negative out, so this has to be a negative beta. So in this case, we have a negative beta. Okay, so I have one angle minus another angle. Okay, so then I have cos 90 minus alpha cos negative beta plus sine 90 minus alpha, I hope you're keeping up, times sine negative beta. Okay, and then the cos and the 90 becomes a sine. The 90 minus alpha means it's in the first quadrant, so we have a positive, and then there's going to be a positive sign. Okay, so we have that. And then cos negative beta, like we said, the cos of a negative angle is equal to positive cos of the angle. So we have that one over there. Then you have plus, so sine 90 minus theta, the sine and the 90 turn into a cos. And it's in the first quadrant, so it's positive, so that's just cos alpha. And then the negative angle, or sine of a negative angle, is equal to negative sine of that angle. Okay, so if we simplify it any further, we will have sine alpha cos beta. We're going to take this negative out, and then we're going to have cos alpha sine beta, and we have it there. Yes. Cool, and that is how we solve. Okay, now getting to the double angles. Okay, so the double angle for sine, let's say we had sine to theta. Okay, you must just know what it is equal to. That's also given in your formula sheet. So that's basically going to be cos, oh, how did we get there? Okay, so we know the answer. It's going to be 2 cos theta sine theta, or 2 sine theta cos theta, doesn't matter. But how did we get there? Basically, we said sine theta plus theta, okay? And that would be sine theta cos theta plus 2 cos theta sine theta, according to our compound angle formulas that we have, right? So if we simplify that, no, why did I put a 2 here? I'm already jumping the gun. Okay, so if I have sine theta cos theta plus cos theta sine theta, that's, you know, I could swap this around, basically. So I would have sine 2 sine theta cos theta, or 2 cos theta sine theta. Okay, so that is how you would get that one over there. If you were now to show the double angle for cos, that's where you have 3 options, remember? So you have cos 2 theta. Okay, we're going to do the same thing. So I have theta plus theta. Okay, then that would be cos theta minus sine theta, because the compound angle for cos is actually cos sine. That's how I remember it. And now we actually have cos squared theta minus sine squared theta, and that's actually one of them. Okay, now remember that identity that we have, that cos squared theta is equal to 1 minus sine squared theta. This comes from sine squared theta plus cos squared theta is equal to 1. So if you were to rewrite it in terms of cos, you have this over here. Okay, so let us substitute what cos is equal to. Cos is equal, or cos squared theta. Cos squared theta is equal to 1 minus sine squared theta. And you also have that minus sine squared theta. So if you were to simplify it, I would have 1 minus 2 sine squared theta. And that would be the second answer or second option for the double angle of cos. Okay, now I also know that sine squared theta is equal to 1 minus cos squared theta. So I would substitute it in this. I have 1 minus 2, 1 minus cos squared theta. If we were to simplify that, I have 1 minus 2 plus 2 cos squared theta. And then if I put the 2 cos squared theta first, I then have minus 1. And that is the third option for the double angle of cos. Okay, so we have covered now the proofs for trigonometry. Okay, now we're getting to Euclidean. Oh, it's gonna be a while. Alright, so we have done paper 1 proofs. We have done part of paper 2, which is trigonometry. So we can take that off the list. And now we get to the circle theorems. Okay, so these proofs, actually you did them in grade 11. Okay. Yeah, you did them in grade 11. If you want to go back, you can. I just got overwhelmed reading all of them and I'm like, oh my goodness, I'm gonna have to do like what, 6 proofs? The only one that I've seen, or the 2 that I've seen where they've asked in matric, but I haven't looked at all papers that have been written ever since. So yeah, I've seen the tan chord theorem being asked for the learners to prove that, and also the angle subtended in the center is twice that at the circumference. Those are the 2 that I've seen. Guys, I'm so overwhelmed to do all these proofs. But let's see how far we get. Let's do it. Let's do it. Also, the proofs that they have really asked in matric, because this is grade 12 work now, when you get to the triangle theorems, they've definitely asked the proportionality theorem. Not so much Pythagoras, hey? Even you had to show that equiangular triangles are similar. That's always asked. Okay, so it's similar to these types where you don't necessarily have to prove, but yeah. Okay, let's do Euclidean geometry. Let's see how far we get. And yeah, let's just do it. Euclidean circles. Euclidean circle geometry. Okay, so what I'm going to do, I'm just going to draw these circles that are required, and then we can prove one by one. And as I'm going through the grade 11 textbook, there are actually somewhere it's written that it's not examinable. So I will tell you which one. For example, number 1, the line drawn from the center of a circle perpendicular to a chord bisects the chord. That's just something that you should know. You don't have to prove it. That's not a requirement. But the one that I've ticked, we have to know. Angle subtended by a chord, that I've seen, that we have to prove. The opposite angles of a cyclic chord are supplementary. The that you should know, but I saw the proof, and then 2 tangents as well. I saw the proof. So we're actually going to do 5 proofs here. Okay. Yeah, let me just take a breather. Alright, so we're starting with proving that the angle at the center, okay, this angle over here, is actually equal to twice the angle at the circumference, which is over there. Okay, so how are we going to start this? Well, you're going to plot a construction line, okay, from P, passing O, all the way to somewhere here, and we can name that Q. Okay, then, yeah, I'm going to use a lot of colors here. This is Euclidean geometry. So now you have an angle over here, okay, which I'm going to name O1, and an angle over there, which I'm going to name O2. Okay, so O1, if I have a look at this triangle over here, okay, if I look at triangle AOP, okay, AOP, O1 is actually an external angle of triangle AOP, and also O2 is also an external angle to triangle BOP. Okay, and another thing that we should also note is that OP is equal to OA because they are radii, okay, in the circle, as well as OP is equal to OB, which are radii. Okay, I'm saying a lot of things. Let me start writing down. Okay, so first we constructed the line Q, or we extended OP to get to the point Q, and now we have O1, okay? So O1, as I've said, okay, I have angle O1, which is an external angle to triangle AOP. So O1 is equal to A plus P, okay, and A plus P, why? Because that is the external angle of triangle, which is equal to the sum of opposite angles, okay. So that is pretty much O1 equal to A plus P. Actually wanted to say it's equal to A plus P in which triangle? Okay, so it's very important that we note which triangle that is in. Okay, so O1 is equal to A plus P in triangle AOP. AOP. Okay. Alrighty. And the very same thing can be said for O2. Okay, that is equal to B plus P in triangle OBP. Okay. Okay, and same reason, external angle of triangle is equal to the sum of the opposite angles. Okay, when you write this in your exam paper, you're gonna write the full thing. All right, what else do we see? Okay, yes, okay, so I did say that OP is equal to OA. OP is equal to OA, okay, because those are the radiuses or the radii. Yes, it's equal to the radius, okay. And if that's the case, we could say then therefore angle P is equal to angle A, okay. Yes, so these two angles over here are equal. Okay, what does that mean for me? All right, So now if P and A are equal, then we can say that O1 is equal to 2P. Okay, so O1 is equal to 2P. That makes sense, right? Because this comes from here. We said that O1 is equal to A plus P. Okay, and now we said P is equal to A, therefore O1 is equal to 2P. And the same would apply for O2. So O2, we have there that P is equal to, okay, so I need to give a reason here. So OP is equal to OA, which is the radius. Okay, therefore angle P is equal to angle A in which triangle? Okay, in triangle AOP. Okay, and what do we then say as our reason? Well, we have an isosceles triangle, triangle AOP, and we know that the sides are actually the same. Okay, so we would then say equal radii. Okay, isosceles triangle. All right, then we can say O1 is equal to 2P, and we can therefore say the very same thing for O2. Okay, so O2 is also equal to 2P. All right, what would be the reason there? So yeah, no, it's fine. So O2 is also equal to 2P. Why? Because we said that O2 is equal to B plus P, and B is equal to P because of the equal radii, isosceles triangle. Okay, so now what can I then say? I can then say if I have O1 plus O2, that would equal to 4P. Okay, and then I could say that in triangle, yeah, so that is equal to 4P. That would be in triangle AOB. All right, and then I could say that in triangle APB, okay, P is actually equal to, I could say 2P, because remember I said P is equal to B here. So I've put that as P, I've put that as P, and we said that A is equal to P here, and I've made both P. Okay, so therefore P would be equal to 2P, if that makes sense. Okay, so therefore we see that the angle in the center, okay, is actually double that of, let me put that as purple. So the angle at the center here, okay, O1 plus O2 is actually equal to, is twice the angle P there. Okay, so therefore we could say AOB, finally, okay, we've proved, so therefore we can say AOB, because we know that O is equal to 4P, okay, is equal to 2 times APB. And that's true because O is 4P and this P is actually 2P. So yes, that is how you would prove it. You would actually show there with the construction. Okay, so just keep the marker alert as to where you constructed what. Okay, so I mainly focused on triangle AOP, but the very same would be applicable for triangle BOP. Okay, so yeah, you could do everything on triangle AOP and say the same is applicable for BOP. Okay, so that's the first one. Now we're going to look at the second one, where angles in the same segment. So basically we're saying if you have a segment AB there, angles from the same or rather angles subtended by the same segment are equal. So we are expecting then that Q is equal to P. Okay, so let us show it. So firstly, it's important to indicate that there's actually a center, okay? We are going to need that as we prove. But this one, to prove that angles in the same segment are actually equal, is not so much of a so bad of a proof. So what we're going to do, because we've already shown that the angle at the center is equal to twice the angle at the circumference, that's where we're going to start, okay? So we know that AOB is actually equal to twice APB. Okay, I hope you see it there. So AOB from here is equal to twice that angle there. Okay, and we also know that AOB, just shift that up, is equal to twice AQB. Okay, and again, I should be giving reasons. So that is angles at center is twice, 2 times the angle at the circumference. Okay, and there's the same reason for that as well. So if both APB is equal to APB and AQB are equal to AOB, we can then say that APB is actually equal to, 2APB is actually equal to 2AQB. All right, and then if we divide by 2 on both sides, well, we have proven actually that APB is actually equal to AQB. So that wasn't so bad, and it didn't take that long. So yeah. Thirdly, we're going to show that opposite angles in a cyclic quad are actually supplementary. Okay, or opposite sides in a cyclic quad, the sum of it is equal to 180 degrees. Okay, so what we're going to do, we're going to construct, so we have a center there. It always helps to have a center. Okay, and we're going to just construct OP over there and also OA. Okay, and once we have that, we can then label this as O1, so that's the angle there, and we can label this as O2. Okay, this side. Now we're going to use the theorem we proved first, angles at center, and then we'll see what that will take us. Seemingly that seems to be working for these proofs. Okay, so we can then say O1, okay, so that's the angle this side, okay, on top, is going to be twice B over there, okay, but B in which triangle? So I'm going to say ABP. Okay, so O1, angle O1 is equal to twice ABP, and our reason there will be angles, or the angle at the center. Angle at the center is twice the angle at the circumference. All right, and now we go to O2. So O2 is this side, okay? So that will be equal to Q, or twice Q, but we're going to say 2 times AQP. Okay, and we have the very same reason. Angles at the center, or the angle at the center, is equal to twice the angle at the circumference. Okay, now I know that if I take O1 plus O2, that I will then get 360 degrees. Okay, so revolutionary angles, or revolutionary angle. Okay, and then what do I do? Okay, so then I'm gonna say 2ABP plus 2AQP is actually equal to 360 degrees. All right, And if I were to take the common factor out, which is 2, and take it to the other side, meaning divide, I would then get that a BP plus a QP is actually equal to 360 divided by 2, which is 180 degrees. And we have then proved, okay, what we were supposed to prove. And similarly, you could do the same for QAB and QPB. It's pretty much the same procedure. All right. Cool. All right, so the fourth one we're going to look at, tangents from the same point are equal. Okay, so yeah, let's just do a little bit of construction over there. So we have OA, which is pretty much the radius, okay? And we have OB, also being a radius. And then we have OP, okay? So now we have two triangles. We have triangle AOP as well as triangle BOP. Okay, and we're trying to show that AP is equal to BP. Okay, so how are we going to start? I would use or try to use similarities. Okay, if I can show that these two triangles are similar, then we can then conclude that AP is equal to BP. Okay, so firstly, I can see when we have a radius and a tangent and they're touching each other, we know that they are actually perpendicular to one another. Okay, so I know that A over there is 90 degrees as well as B. That's also 90 degrees. Okay, so I can then start by saying OAP. So A in triangle OAP is actually equal to 90 degrees, which is also equal to OBP. Okay, so both A and B are equal to 90 degrees. Okay, and that's basically the reason would be the radius is tangent. Oh, sorry, it's perpendicular to the tangent line. Okay, now what can we do then? We could say that OA is equal to OB because that's pretty much the radius of the circle, radii of the circle. Okay, so I know those two are equal, we have equal angles as well. All right, and then I could then say OP. So yeah, well, in triangle AOP, and triangle BOP, AP is like the, sorry, OP, not AP. So OP is like the similar side. Okay, so yeah, if I were to sketch these two triangles separately, I would then conclude and I would show that actually triangle AOP is similar, we indicated with these lines. So AOP is similar to triangle BOP. Okay, and the reason would be side, angle, side. Okay, because we showed the sides, which are the radii first of all, angle, okay, which is the 90-degree angle, and also the common side or the similar side. Okay, so side, angle, side. So therefore we can then say that AP will be equal to BP. Okay, so yeah, I think that is it. And then we're going to have a look at the last one, the tan-chord theorem. So far this year, I've seen them ask this question twice for the prelims as well as the November exams. I don't know if they'll be asking it next year, but it's always good to know. So we'll start by constructing the line from the center. Okay, so we have from the center to the tangent. Okay, so we have a radius there, right? And that would be 90 degrees, okay? But I'm also going to extend it such that we have a diameter, okay? And then we'll call that point T, all right? And then if you know that the angle subtended by diameter will be actually 90 degrees, so if we took it to Q there, we would have 90 degrees also there at Q because our diameter is the chord. And also if you were to extend it over to A, you would see that A is 90 degrees in triangle ABT, okay, because of the diameter being your chord. All right, so let us just start writing. So what I would say initially is that OBS, okay, or TBS. Okay, so TBS is equal to 90 degrees. Okay, then I would look at the angle ABS. Okay, so I would say let ABS equal to alpha. Okay, so let me choose another color. So this would be alpha. Okay, and then if I were to look at TBA, that would be 90 minus alpha. Okay, so let ABS equal to alpha. Okay, therefore TBA will be equal to 90 minus alpha. Oh, I forgot to write here, TBS is equal to 90 degrees. That is because we have a radius that is perpendicular to our tangent. Okay, tangent. Okay, and then TBA is 90 minus alpha. Well, those angles complementary. Okay, complementary angles. Okay, sum of complementary angles is 90 degrees. But yes, so TBA is here, so that is 90 minus alpha. Okay, how does that help us? We want to show that B over here, our alpha, is actually equal to Q over here, right? Yeah, that's what we want to show. So now let us have a look at our graph again. So if I focus on triangle ATB, what do I know? Okay, so in triangle ATB, okay, I know that A is equal to 90 degrees. Okay, diameter, so the chord is the diameter. Chord is diameter. So chord is diameter. Therefore, angle subtended by it is 90 degrees. Okay, so we know that A, and we know that B, we've already said it, B is actually equal to 90 minus alpha. Okay, so therefore, what would T be? T would be 180 minus 90 minus 90 minus alpha, and that is due to sum of angles in a triangle. So the sum of angles in a triangle are equal to 180 degrees. Okay, so let's just work out what T is. So T, 180 minus 90, that is 90. And then we have minus 90 and we have plus alpha. So we have that t is alpha. Okay, so we can put it in there. T is alpha. Okay, now we have a cyclic chord here. When we constructed t, our cyclic chord was ATQB or ABQT. Okay, so in the cyclic chord, so we have a common, we have a chord here, chord AB, all right? So chord AB, it subtends both Q and T, okay? So therefore I could say Q, or rather, let me say AQB. So let me say AQB is equal to T, which is equal to alpha, which is now angles subtended by the same chord. Okay, so that would mean then, remember that we said ABS is also equal to alpha, right? We already mentioned that at the beginning. Let ABS equal to alpha. So at the end, we could say therefore ABS is equal to AQB. Okay, and that's basically the 10 chord theorem. Okay, ooh, that was quite long. But basically, when you have your triangle in your circle, make sure that the triangle is actually touching the circumference, the corners of the triangle, the vertices. So you then construct T, okay? Then you define, in this case, we define B from ABS. And yeah, the rest just comes into place. So with more practice, it will come naturally to you. But that is the 10 chord theorem. Like I said, it has been asked quite a lot this year, twice as a lot. So yeah, that's one to check out for. But yeah, basically we're done with the circle geometry proofs. Yo, finally, now we can get to the proofs for grade 12, which is the triangle theorems. Okay. Alright, so we have reached the final proofs, and that being the proofs of triangle theorems. Okay, the first one we're going to look at is the proportionality theorem. Okay, so a line drawn parallel to one side of a triangle divides the other side or the other two sides proportionally. Okay, so here we have two parallel lines. We have DE parallel to BC. Okay, it's given that, okay, triangle ABC with DE parallel to BC such that D lies on AB and E lies on AC. Okay, so firstly, before you even continue, you need to draw some construction lines. Okay, so let us do that. Okay, all right, so we are going to divide the bottom part, which is like a trapezium here, BDEC, okay, or BCDE. So basically we will divide it like this. So you have DC over there, okay, such that you have triangle DEC, and then another crossing over there. Just gonna make it this color. Okay, so yeah, you have those construction lines. Actually, let me do it like this rather, so that it looks prettier than what I'm doing here. Okay, much better. Let me just use the same color. Okay, so yes, those are construction lines, and as well, okay, but yeah, let's leave it at that and then begin with this proof. I've also seen this proof. I don't know if it was the prelims or the June sub, but they have asked this question. Okay, so now we need to prove like AD over DB is equal to AE over EC. Okay, so what I'm going to look at first, I'm going to look at triangle ADE. All right, I'm going to try to get the area of triangle ADE as well as the area of triangle DBE. Okay, so let's start. So we have the area of triangle ADE, okay, and I want to see with respect to the area of triangle DBE what that would be. Okay, so if I'm going to get the area of a triangle, I'm gonna have to get this is gonna be half base times height. Okay, so half, what is my base here? I'm gonna take AD as my base. Okay, so AD will be my base. Okay, and then I'm gonna look for a perpendicular height. So why I'm doing this and making AD my base instead of DE is because I want to end up with AD here on top. Okay, so I need to get a perpendicular height for both triangles ADE as well as triangle DBE such that the perpendicular heights can cancel. Okay, so I have AD as my base, and then my height, if I take a perpendicular line and then I construct there the height, so the height would do something like this. Okay, and that would be perpendicular, the perpendicular height. So you see, for triangle ADE, I have a perpendicular height. I'm gonna name that height H1. All right, so I have H1 over there. Now if I look at triangle DBE, okay, this is my base DB, okay, which is in the same line as AD. All right, so I'll have half DB. Okay, and I see I have DB over there, which is good. And then my perpendicular height, okay guys, please be careful, the perpendicular height will not be DE. Okay, the perpendicular height will be H1. Okay, all right, so when I do that, I will have the halves cancelling and H1s cancelling, so I'm left with AD over DB. So we're getting somewhere here. Okay, and then I'm going to do the very same thing. I'm still looking at area of triangle AED. Okay, it's AED. I'm going to say AED this time. AED, because I'm looking at the AE here. All right, so AED or DAE, doesn't matter. So area of triangle AED over area of triangle ECB. Okay, so same thing here. If I'm going to take my base as AE, as you see there, so we have half base AE times height. Okay, so there again, I'm going to have my perpendicular height, which would do something like this. So these would be your construction lines on these drawings here. I don't know if they expect you to draw them in or if they have them in for you, but this is what you're going to do. Okay, so now, oh, I forgot to put there what that height is. I'm going to call that H2. Okay, so that was H1 and this will be H2. And then same thing, so I have my base there and my height is H2. Okay, and then also I have half EC, the triangle at the bottom, times my perpendicular height. Wait, where am I now? This looks kind of funny. What did I do? Okay, so AE, this is my base. Yes, H2. I'm looking at H1, like how is this a perpendicular height? It's H2. Okay, so I have H2 there, and then yes, it's also the perpendicular height for triangle ECB. Okay, so yes, and now that is H2. Okay, and if everything that is supposed to cancel cancels, we are left with AE over EC. Okay, so we are getting somewhere here. We have the stuff that is needed, but how do I then now show that AD over DB is equal to AE over EC? Okay, let's look at the trapezium BDEC or CBDE. Okay, so here, okay, let's see. Okay, just an error I made with this triangle here. It's actually ECD. Okay, not ECB. So here we had D, B, E. So here we're going to have E, C, D. Okay, not B. All right. So now, what do I have? What do I see here? I can actually see that triangle A, not A, triangle DBE is actually equal to triangle ECD. Okay, so D, yeah, triangle ECD. And why do I say that? Why are these two triangles equal in size? Well, basically they're sharing the same base, okay? So it's basically, if I'm looking at DBE, it's this triangle here, okay, with this over there, okay? Yeah, this triangle DBE and also the triangle ECD, okay? So how do I know that they're equal? They have the same base. If I take DE as my base, that's the same, okay? So they're equal because they have the same base, which is DE, okay? And they also have the same perpendicular height, okay? You know that when you have parallel lines, the height is the same, okay? So this height here, perpendicular height, is actually the same throughout, okay? So same base and same perpendicular height, okay? So perpendicular height. All right, so if I were to get the area of DBE, I would say half times my base, which is DE, times a height H. Same thing here, I would get half times my base, which is DE, times my height, so hence they are equal. Alrighty, now I need to show, like we said, prove that AD over DB is equal to AE over EC. Well, if I then say triangle, so the area of triangle AED, or rather ADE over the area of my triangle DBE, the area of triangle ADE, do you realize that it's the same as the area of triangle AED, because they are the same triangle in essence? So I can therefore say that area of triangle ADE is equal to the area of triangle AED. Okay, why? Because that is the same triangle. Okay, and then I've just proved that the area of triangle DBE is actually equal to the area, oh, I forgot to put areas here, area as well as area. Well, it's equal to the area of triangle ECD. Okay, yes, that has already been proved. Okay, so therefore, guys, I can say that area of triangle ADE, that's AD over DB, that would be equal to AE over EC. Okay, and that is what we have done here. We have proved it. Okay, this wasn't so bad. But yeah, basically it helps when you put construction lines. Like I said, I don't know in what condition they're going to give you this triangle over here. It just might be very clean and you have to put in the construction lines yourself, or they might have the construction lines for you, which I highly doubt. But yeah, please get to practice this and ensure that you know it and you understand it. Like I said, I've seen it quite a couple of times. So yeah, don't leave anything to chance. Okay, so let's look at the next one. All right. Okay, here I'm removing things. Okay, so that is C and that's A. All right, let's go have a look at what is next. Okay, now it says if two triangles are equiangular, their corresponding sides are in proportion. Okay, so we need to prove that DE, okay, so here is DE over GH, okay, there's GH is equal to DF, okay, there is DF over GK, which is equal to EF, okay, over HK. Okay, cool. So let us attempt this. And what has been given? It has been given that triangle DEF and triangle GHK has been given with D being equal to G. So I've placed there an X to show that the angles are the same. E is equal to H. I've placed a Y there to show that the angles are the same. And then F is equal to K, which I've placed W there as the angle. Okay, so let us see how we are going to solve this one and prove that the corresponding sides are actually in proportion. So one of the things you're going to have to construct, which I've already constructed for us, is a line called MN. So that construction line MN, you need to ensure that MN is actually equal to HK, okay, such that you eventually have DM being equal to GH and DN being equal to GK. Basically, triangle GHK being congruent, okay, or identical to triangle DMN. Okay, so what are we going to start writing? We're going to say that in, let me get my blue pen. So, in triangle DMN and triangle GHK, okay, we have that DM, yes, so we have DM there. We have that DM is actually equal to GH, all right, and that's due to the construction that we have made there. Okay, and then we have that DN is actually equal to GK. Again, construction. All right, and then we know that from what was given that G is actually equal to D. Okay, so that was given. Okay, and therefore what can we conclude? We can therefore say that triangle DMN is actually congruent. Okay, congruent is like 3 equal signs. Okay, it's actually congruent to triangle GHK. Okay, if they're congruent, it means that they are identical. Okay, the sizes are the same, the angles are the same, unlike with similar triangles where they have similar or rather the same angles but not the same size. The sizes are proportional. Okay, so we can then say triangle DMN is congruent to triangle GHK. And if that's the case, we can then also conclude that M is actually equal to Y. Okay, so that would be equal to Y. Okay, because the value of M is equal to the value of H. Okay, because we've proved congruency. And in proving congruency, we can then say that angle angle H is equal to angle M, which is equal to angle E. Okay, my handwriting. Yeah, it's equal to E. And because of that, all right, so we have said that M is equal to E, and we have said that MN is parallel to EF. Okay, they are both parallel. Okay, and now let's just remind ourselves. Let me just take this over here and see what it is that we actually have to prove before we go on a tangent. Okay, because we want to match. Whenever they tell you to prove something, you want to make sure that you are matching the thing that they're telling you to prove. Okay, let me just make that red. All right, so we're trying to prove that DE over GH, so DE is the entire length, okay, over GH is equal to DF over GK. Do we have something like that? All right, so yeah, then I want to use the proportionality theorem. Okay, the proportionality theorem here, because we have these two parallel lines, we can use it, right? So if we say DE over DM, how would that look? So DE over DM, okay, is actually equal to DF, okay, DF over DN, okay. So currently we have this portion over here, DE, and we have DF. Now, didn't we say that DM is actually equal to GH? Yes, we did over here. Okay, so we can rewrite it. Oh, first of all, we need to give a reason there. So proportionality theorem, okay, where we have that MN is parallel to EF. Okay, so now we have DE, and in place of DM we can put GH, okay, and then we have DF, and in the place of DN we can put GK. Alright, so we have found this part here, okay. Now we need to show that EF, where is EF? Okay, so this portion over here, so EF over HK, okay, that they are also in proportion. All right, let's see how we are going to do that, such that we can then say that DF over GK is equal to EF over HK. All right, yeah, let's see. So we have shown that DE over GH is equal to DF over GK with the construction that we did here, okay? All right, because we saw that this is where DE is and this is where DF is, okay? But now the last portion is about EF over HK. So you're going to take the same triangles, okay? And then you're going to reconstruct it a little bit such that it looks like this. So GHK remains the same, but now remember we had the triangle over there previously, right? Yeah, but now we're going to shift it this side. Let me just go back. We're going to shift it there so that we can show that these lines are actually parallel. We can use the proportionality theorem, and then we can prove that DF over, okay, DF over GK, okay, is going to be equal to EF, which is this part at the bottom, over HK. Okay, so yeah, let us try to do that. We can show again, what is it called? Congruency. Okay, so then we can say that EA, just by putting in A and B, we can say that EA is actually equal to HG or GH, okay? And that is due to the construction that we did, okay? And then we can also show that EB is equal to HK, okay? Again, construction. And then it was given to us that H is equal to E, which is equal to Y, okay? So therefore we have side, angle, side, okay? So therefore we can say triangle ABE is congruent to triangle GKH. Okay, just trying to make sure I'm using the same letters, corresponding letters. Okay, and if they are congruent, it means they are identical. All right, so therefore, I can then say A is equal to X. Okay, yeah, I could say A is equal to X, B is equal to W. All right, so therefore, I could say that A is equal to G, or G is equal to A, which is equal to D, which is equal to X, okay, because we've shown congruency, all right, and therefore we can then say that DF or AB is equal, or rather AB is parallel to DF, okay, and that is due to A being equal to D. Okay, how did we write it there? Yes, corresponding angles. Alrighty, so we have our parallel lines over here. That means we can then use the proportionality theorem. Okay, so what are we left with again? We're left with EF. Okay, and you want to say DF. Where is DF? Okay, DF. Alright, so we could say then that DF over no. Let me put it this way. I could say DE. I can use DE because now there's proportionality. So I could say DE over EA. Okay, over EA is actually equal to EF. We're looking for EF, right? Yeah, EF is the last one. Is equal to EF over EB. Okay, and that's due to the proportionality theorem, where AB is parallel to DF. Okay, and then we know that DE, all right, that actually EA is equal to HG, right? We had proved there due to construction. So we can say that DE over GH instead of HG, okay, is equal to EF over EB. We can put it as HK. Okay, let's see. EF, yes, HK. All right, and things are coming together. Sorry, I'm squeezing things in there. Okay, so yeah, so therefore we can then say, do you see that we now have our last part, which is DE over GH is actually equal to EF over HK. So therefore we're done proving this, guys. We can then say, therefore DE over GH is equal to DF, right, over GK, which is equal to EF over HK. Okay, so it took a bit of a while, but basically, guys, the thing about this question is construction. Okay, you're trying to construct it such that you can use the proportionality theorem. All right, just like the previous one as well. You wanna, okay, this is the proportionality theorem, but you want to use the proportionality theorem here to prove, okay, that the corresponding sides are in proportion. All right, and then we have a look at the last proof. And then we're done with these proofs, guys. I'm so tired of them. Let me just take this a bit lower, and then we can discuss. Okay. Let's see what it is that they want from us. Alrighty, so this is Pythagoras' theorem using similarity. Okay, so I see that I didn't put in an S there. Using similarity. Okay, so basically you want to show or prove that triangle PQR, that is the big triangle, is actually similar to triangle TPR. So TPR, which is actually similar to triangle TQP. Okay, so TQP. And I've seen questions like this where you have a huge triangle and then you have these other triangles and you need to show that all of them are actually similar. So what is similarity? That's basically having the same angle and the sides being in proportion. Okay, yeah. So we are given that triangle PQR with, we are given triangle PQR with P in QPR is equal to 90. Okay, so we have that 90 degree there. All right, and then we have that PT is perpendicular to QR. Okay, so we also have 90 degrees. Hence, we have like 3 90 degrees. 3 right angle triangles. So, yeah. So anyway, now let us, okay, so let's just say let Q be equal to X, okay? So if we put X there, in the big triangle, for the big triangle, let me use a different color. Let me use purple, okay? So if Q is X in the big triangle, we have 90 degrees there, okay? Then we have X, okay? How are we going to get R? Well, basically, P plus Q plus R would be 180 degrees, right? And that is the sum of angles in a triangle. Okay, so P, we have it as 90 degrees. Q, we have it as X. Okay, and we have R, and all of that is 180. Therefore, R would be equal to 180 minus 90. That would be 90, and then minus X. Okay, so R there we have it as 90 minus X. That is for the big triangle. Now for the smaller ones, if, let's say this is the smaller one here, PTR. Okay. Yeah, so for the purple, that this, all of this was for in triangle QPR. Okay, now if we were to look at triangle PTR, okay, so in triangle PTR, okay, we know that T is equal to 90 degrees. That was given. Okay, and then we know that R is equal to 90 minus X. That was previously solved. Okay, so what would P be? Well, P will just have to use the sum of angles in a triangle being 180. Okay, so again, sum of angles in triangle. Okay, so we know that T is 90, so I'm left with 90 as is, and then R is 90 minus X. Okay, so P is actually X. Alright, so let's see. So this is X. Okay, And then if we have a look at the other triangle, QPT, okay, indicate it like this. Okay, so in triangle, let me put it on this side. In triangle PQT, okay, I have that T is equal to 90. Okay, that was given. Okay, oh, by given I mean that because we had PT is perpendicular to QR. Okay, PT perpendicular to QR. Okay, hence the same reason over here. So we have T is equal to 90, we have that Q is equal to X. Okay, and now P will be 90 minus X. Okay, so now we have our, okay, yeah, we've put everything that we can. Okay, so now let us see if we can show similarity. Okay, so what I'm going to try to do, if I redraw all of this in my big triangle, which is blue, I'm gonna sketch it like that, where P is where I have my right angle triangle, and I'm gonna put Q there, and I'm gonna put T. So I know that T in this, no, there's no T here. So it's P as the right angle triangle, and I have Q up there, so I have R. Okay, I know that R is 90 minus X because Q is X. Okay, then I have the smaller one. Okay, this should have been purple because the bigger triangle is purple. Okay, now we have the smaller triangle, which will be red. Okay, I'm gonna put it on the side there. I'm also gonna put it like that. So I have T, right? I have R, and then I have P. So I know that P is X, T is the right angle, and then R is 90 minus X. Okay, then I have the other one remaining, other small triangle remaining. I'm also going to draw it like that, where I have T as well. I'm actually going to put Q up there. I'm going to turn it around, rotate it, okay, and I have P. Rotate it and flip it. Okay, so T is 90 degrees, P is 90 minus X, and Q is X. Whew. Okay, so now with all of this, something must give. Okay, so I can actually cut this, and we can put it somewhere below and then conclude and be done with these theorems. Okay, so I drew it this way to make it easier for myself so that I can show similarity. Okay, let's just see. Let's just get what we need to prove such that we are corresponding with it, because we also need to be aware all the times what it is that we are trying to prove here. Okay, this is what we're trying to prove. So I'm going to start with P. Okay, in triangle PQR, okay, PQR, I know that P is equal, so this is P in PQR, okay, P is equal to T, which is equal to T, okay, and all of them are equal to 90. Okay, so I have the P, I have the T, I have the T. Great. Now, let me start with Q in triangle PQR. So Q, there is Q, it's equal to P in triangle TPR. Okay, it's equal to P, and it's equal to Q in triangle TQP. Okay, so that is equal to X. Alrighty, and then lastly, okay, we have R. Okay, so we know that, oh, let's take it off. We have Q, we have P, we have Q. Okay, great. Now lastly, we have R. Okay, so R is equal to R in triangle TPR, and is also equal to P. Okay, so R equal to R, and it's equal to P, which is equal to 90 minus X. Okay, so things are working out. Therefore, we can then conclude that triangle PQR, okay, triangle PQR is actually similar to triangle TPR, which is actually similar to triangle TQP. And that is it. That's it. Thank you. Yeah, that's it. I think those are all the proofs that you need to know. They're not bad. It's just there are many. And I know when you're studying and sometimes you run out of time, and these are the last things that you look at. So hopefully this video will help you just to browse through it quickly and remember when you are in the exam. Okay, so have yourself a lovely day further. Please don't forget to like our videos, subscribe to our channel, click on that notification bell, and visit our website if you want a private lesson at www.mvtutors.co.za. Okay, bye.